Welcome back to the lecture on sequence and series. To begin with, let us recall an arithmetic progression which we defined in the last lecture. Let us call AP in short. Recall that an arithmetic progression is a sequence such that the difference of any two consecutive terms remains the same. To put in simple, a sequence n ranging from 1 to infinity is called an arithmetic progression if an plus 1 is equal to an plus d for all integers greater than or equal to 1. This essentially says that the difference of two consecutive terms, namely an plus 1 and an, is d, where d is a constant. The first term a1 and the common difference d determines the arithmetic progression completely. That is, if n is equal to 1 to infinity is an arithmetic progression with a1 is equal to a, called first term, and the difference between two successive terms is d, called the common difference, then the arithmetic progression can be written in standard form. As follows. A, the second term will be a plus the common difference d, the third term will be a plus 2d, and so on. Observe that between n terms there are n minus 1 successive common differences. Hence, or otherwise following this pattern, it is not hard to see that nth term of this AP, namely AP with first term a and common difference d, is given by the formula a plus n minus 1 into d. Next, let us observe some properties of an arithmetic progression, of which we have discussed first property in the last lecture. Let me remind you, if n is equal to 1 to infinity is an arithmetic progression, then sequence Bn obtained by adding same number to each term of the given AP. That is, the sequence Bn where nth term Bn is equal to An plus some k for every n is again in arithmetic progression, Essentially, this property says that we can create an arithmetic progression from a given arithmetic progression by adding a constant to each term. Second property is very similar. Instead of adding a constant to each term, we can subtract, or in other words, this k can be positive or negative. To be explicit, let me list it. If n is equal to 1 to infinity is an arithmetic progression, then the sequence Bn obtained by subtracting a constant, say k, to each term is again a arithmetic progression. So, let us write Bn is equal to An minus k for every n starting from 1. The claim is that sequence Bn is an arithmetic progression. To continue, let us have a similar property. If sequence n is equal to 1 to infinity is an arithmetic progression or an arithmetic sequence, then sequence obtained by multiplying each term of sequence An with a constant is again an arithmetic progression. Though it is straightforward, let us work out the details. Our assumption is that An is an AP. It means An plus 1 minus An is a constant, let us call it as D, for every n element of set of natural number n. Using this given sequence, let us construct a new sequence Bn. Consider sequence Bn, n equal to 1 to infinity. How do we construct Bn? We just multiply An with a constant. let Bn is equal to some C times An for every n. We have to observe that this sequence Bn is again in arithmetic progression. Let us do that. Consider the difference of two successive terms in Bn, namely Bn plus 1 minus Bn. This will be C times An plus 1 minus C times An, which is C times An plus 1 minus An. As An forms an arithmetic sequence, An plus 1 minus An is a constant for all n. Hence, we get C times D. So, what we observe, for all natural numbers n, the difference Bn plus 1 minus Bn remains a constant. This establishes the fact that sequence Bn is an arithmetic sequence. But unlike in the other case, where we constructed a sequence from the given arithmetic progression by adding constant to it, here the common difference of the constructed sequence is different from the common difference of the given arithmetic progression. See that the difference An plus 1 minus An is D, whereas the difference Bn plus 1 minus Bn is not the same D, but it may be different from D depending upon what is this C. Similar result can be told for division. Let me quickly write it here. If sequence An, n is equal to 1 to infinity, is an arithmetic progression, then sequence Bn obtained by dividing each term of sequence An with a non-zero constant. Remains to be an AP. Given an AP, you can divide each term of that AP with a non-zero number. You can obtain a new sequence, and it's not hard to see that the new sequence is again an arithmetic progression. To sum up, we can construct an AP from a given AP by adding constant to each term, by subtracting a constant from each term, by multiplying a constant with each term, or by dividing each term by a constant. In the case of division, make sure that the number with which you are dividing is non-zero. Now, let us ask the following question. Let A comma B be given numbers, given real numbers. Can we insert a number let us call it as capital A, such that A given number small a, this number capital A which we would like to insert, and the given number B are terms of an arithmetic progression. So, this is the question we would like to address right now. You are given with two real numbers. Let us denote it by small a and small b, and we are asked to see whether we can come up with a capital A such that small a, capital A and small b becomes three consecutive terms of an arithmetic sequence. Observe that for an arithmetic progression or an arithmetic sequence, the difference of any two successive terms should remain the same. With that basic principle, or we can answer this question. Since A, capital A and B are to be in AP, the difference, namely capital A minus small a, should coincide with the difference small b minus capital A. This reads off 2a equal to a plus b, which provides capital A equal to a plus b by 2. Thus, given two real numbers small a and small b, it is always possible to get a number capital A such that A, capital A and B are terms of an arithmetic progression, and the capital A is given by a plus b by 2. Let us make a definition here. Given two numbers small a and small b, the number a plus b by 2 is called arithmetic mean. AM for short, of A and B. Let me put in simple. Arithmetic mean of A and B is given by A plus B by 2. You have observed previously that when two numbers are given and we insert arithmetic mean between them, then the three numbers can become three consecutive terms of an arithmetic progression. Having said this, let us ask a slightly general question. Question is this: instead of inserting one number between given two numbers small a and small b, can we insert finite number of real numbers so that the given two numbers and the inserted numbers altogether can successive terms of some arithmetic progression. Let me write it for you. Let A and B be two numbers given. What is the question? Can we insert numbers, not just one number, but finite number of real numbers? Let us call A1, A2, etc. an, so that A, A1, A2, an and B are successive terms of a sequence which is an AP. So, given two numbers A and B, we would like to insert n numbers between them, so that the n plus 2 numbers altogether are successive terms of an arithmetic progression. Let us try to answer this. Recall that the requirement is A, A1, A2, etc. an and B are in arithmetic progression. Means these terms are some consecutive terms of an arithmetic progression. So, altogether we have n plus 2 terms with B as the n plus 2th term of that AP. Recall, given the first term small a and common difference D, n plus 2th term can be obtained using a formula. The n plus 2th term by formula is a plus n plus 2 minus 1 into D, where D is common difference of the AP for which these n plus 2 number should become consecutive terms. That is, B should be equal to A plus n plus 1 into D. Since B turns out to be the n plus 2th term, B should coincide with A plus n plus 2 minus 1 into D. Working out, this gives D equal to B minus A by n plus 1. Recall, to describe an arithmetic progression completely, what we need is the first term and the common difference. Here the first term is given number A, and we have just now obtained the common difference D as B minus A by n plus 1. Thus, the second term, that is the first number to be inserted, capital A1, will be A plus D, which is a plus b minus a by n plus 1. The second number to be inserted, namely a2, that is going to be the third term in this arithmetic progression. Hence, a2 is a plus 2d, which is a plus 2 into b minus a by n plus 1. In a similar fashion, you can write a3, which is a plus 3d, and that will be a plus 3 times, plug in the formula for d, namely b minus a by n plus 1, and so on. The last number that we wish to insert in simple an is equal to a plus n into d, which is a plus n times b minus a by n plus 1. Thus, given any two numbers, we can always insert finitely many real numbers between them, so that the given numbers along with these inserted numbers can turn out to be successive terms of an arithmetic progression. So, let me sum up. We have looked into the definition of an arithmetic progression, a sequence such that difference between any two successive terms remains constant is said to be an arithmetic progression. Standard form of an arithmetic progression with first term small a and the common difference d is a plus d, a plus 2d, and so on. The nth term an is given by the formula a plus n minus 1 into d. Given two numbers a and b, arithmetic mean of a and b is given by the formula a plus b by 2. This is just for a quick recap. Next, let us ask the following question. Let an arithmetic progression with first term a and common difference d is given. Let us take it in its standard form a plus d, a plus 2d, and so on. The question that we want to answer is the following. What is the sum of first n terms of this AP? In simple, we want to get a expression for a plus d plus etc. up to nth term, namely a plus n minus 1 into t. can we have a closed form expression for this? That's what we want to investigate next. Before answering this, let me share an anecdote with you. This is a famous story about Carl Friedrich Gauss, popularly known as Prince of Mathematics. The story goes like this. Gauss was punished by his teacher for his misbehavior. What was the punishment? The punishment given was find the sum of first 100 natural numbers. So easy to do it, right? But let me remind you, this was when Gauss was fairly 5 years old. Surprisingly, Gauss could come up with an answer in matter of seconds. Now, how on earth he could come up with sum of first 100 natural number within second, that too at the age of 5 years? He used a brilliant trick, and the trick is grouping these 100 numbers. Let me give you an outline. He listed the 100 natural numbers 1, 2, 3, etc. up to 100. May not be written fully, but then he could see that these 100 numbers can be grouped in the following way. Group 1 and 100 together, group 2 and 99 together, group 3 and 98 together, and so on. Is pairing the 100 numbers. Do you observe that sum in each pair is 101? The sum of 1 and 100 is 101. Sum of 2 and 99 is 101. Sum of 3 and 98 is 101, and so on. So, sum in each pair is 101. How many pairs are there? Recall, there are 100 numbers, so there are 50 pairs. And each pair sums to 101. So, total sum will be 50 pairs are there, with each pair summing to 101. So, it is 50 into 101, which is 5050. This is how Gauss could compute sum of first 100 natural number in matter of second. No doubt it is a remarkable fact that at the age of 5 years he could conceive the idea. And the same idea of brilliantly pairing and adding is what we are going to do to answer the question I posed slightly before. What was the question? What is sum of n terms of the arithmetic progression a plus d, a plus 2d, and so on? Let us answer this with the idea Gauss used to sum 1 to 100. Let us denote the sum of first n terms of an arithmetic progression by Sn. So, Sn is notation I use for a plus plus a plus d plus etc. plus the nth term. Remember, nth term of an AP with first term as a and common difference as d is a plus n minus 1 into d. And what we are looking for is a formula for this sum, Sn equal to a plus d plus etc. plus a plus n minus 1d. Since we have only n terms in our consideration, let me call the nth term a plus n minus 1 into d as the last term, and let me denote it by L. So, we want to find Sn equal to a plus d plus etc. plus L. Remember the idea of summing first 100 natural number. We have grouped it. Adapting it maybe with a slight modification, we can write Sn also as, remember Sn is a plus d plus etc. plus L. This can be written also as the last term L plus the term previous to L. Can you tell what it will be? L minus the common difference, isn't it? Plus previous to it L minus 2d and so on. We will reach up to the first term A. So, instead of writing from A to L, we are writing from L to A. Now, let us add both these expressions. Sn, sum of first n terms starting from A and ending with L, and sum of same n terms but now starting from L and ending with A. Let us sum these two. Left hand side gives you 2Sn. So, 2Sn equal to, do you see that A and L adds up to A plus L? Similarly, the second term A plus D in the first expression and the second term L minus D in the second expression adds up to give A plus L. D gets cancelled and so on. The last term in the first expression is L and the last term in the second expression is A, which adds up to L plus A. Please look at 1 and 2 again and compare the corresponding terms in the right hand side expression. First term in first expression is A, first term in second expression is L, they added up to A plus L. Second term in right hand side of first expression is A plus D, and second term in right hand side of second expression is L minus D. They add up to give A plus L and so on. So, A plus L and so on A plus L. And how many are there? N terms. Thus, we get 2Sn is equal to n times A plus L. We want an expression for Sn rather than 2Sn. So, let us write Sn equal to n by 2 times A plus L, and this gives you a formula. Sum of first n terms of an arithmetic progression is given by n by 2 into first term plus last term in consideration. It is an important formula. It can also be written as Sn equal to n by 2 into a plus. Remember, L is the last term in consideration. We are considering n numbers. So, L is actually the nth term of that AP, which is a plus n minus 1 into d. So, by a little arithmetic, we can see that it is n by 2 times 2a plus n minus 1 into d. This gives an alternative formula for a sum of first n terms of an arithmetic progression. First one can be used if you are supplied with an AP and precisely we can detect the first term and last term. Whereas the second one we can use if first term and common difference is known and number of terms is given. Having said this on AP, let us proceed to another type of sequence, special sequence called geometric progression. Recall that in arithmetic progression, the difference of two terms, two successive terms, remains a constant. Instead of difference of any two successive terms, if the ratio of any two successive terms of a sequence remains constant, we call that sequence as geometric progression. Let me write the definition precisely. A sequence n is equal to 1 to infinity is said to be a geometric progression GP for short if no terms are 0 and an plus 1 by an, the ratio of two successive terms is equal to r for every n element of n. Let me repeat. A sequence an of non-zero real numbers is said to be a geometric progression if the ratio an plus 1 by an remains constant irrespective of n. You take ratio between any two successive terms, a term divided by its preceding term, it should remain the constant. Please note the condition that no term of the sequence is 0. That facilitates this division an plus 1 by an. For instance, consider the sequence 3, 6, 12, 24, etc. Can you observe the pattern? The second term is first term multiplied with 2. Third term is second time multiplied with 2, and so on. To put in other words, the second term by first term 6 by 3 is same as the third term by second term 12 by 6 is same as fourth term by third term, and so on. Here an plus 1 by an is equal to 2 for every n, with the assumption that this pattern follows. Similarly, consider the sequence 1 by 2, 1 by 4, 1 by 8, 1 by 16, etc. Let me write a general term 1 by 2 power n, etc. 1 by 2 power n, etc. Here also you can see that ratio of two successive terms remains the constant. Let us recall the definition. A sequence of non-zero terms is said to be a geometric progression if an plus 1 by an is equal to r for every n element of n. This r, the ratio of any two successive terms which remain constant, is called common ratio. Similar to an arithmetic progression where the first term and the common difference completely describes the progression, in case of GP, the first term and common ratio completely describes a geometric progression. If first term is A and common ratio is R, then we can write GP in standard form as A, remember an plus 1 by an is R. So, an plus 1 is r times an. So, the second term will be r times the first term. The third term will be r times the second term, which is r square a, and so on. So, standard form of a geometric progression with first term a and common ratio is r is given by a, ar, ar square, and so on. Following the pattern, you can see that the nth term of this GP in standard form is the following: a r power n minus 1. This is the expression for nth term of a GP with the common ratio r and first term a. Similar to the case of arithmetic progression, let us ask the following question. Can we get a closed form expression for sum of first n terms of a GP? Consider the GP A, AR, AR square, etc. nth term AR power n minus 1, etc. Can we get a formula for Sn? Denotes the sum of first n terms A plus AR plus etc. plus AR power n minus 1. We will develop the formula in the next class. Here we will adopt a slightly different technique. Recall that in the case of AP, we use the technique or the trick of grouping properly. Here we may use a different technique to develop a formula for Sn. Next class we shall establish the formula and explore GP and AP further. Thank you.